All right, guys, I'm going to walk you through the first five that I assigned on Monday. You should be through those now. If not, then follow me on this. So anyway, number one, block of mass 2.5 kilograms sliding across a smooth level surface at 3 meters per second when it hits a stationary spring bumper. Fixed at one end as shown. Force constant that's the stiffness of the spring. The force constant is 360 newtons per meter. What amount does the block compress the spring? So you start these conservation problems by saying the total energy initially has to equal the final total energy. What types of energy do we have in this situation before? Well, it's moving, so we know it's got some kinetic energy. It's got no height, so I'm not going to put any gravitational energy. As a matter of fact, we don't have to worry about gravitational energy at all. Nothing's jumping up or down in this problem. Also, initially, it's not touching the spring. So until it starts to compress the spring, there is no elastic potential energy, no spring energy. When it compresses the spring and comes to rest, you've got no kinetic energy on the right side. On the final side, it is all stored in elastic potential energy, right? So we go from a moving block initially to a stationary block that's compressed to spring. So we go 1/2 mv squared on the left, 1/2 kx squared on the right. That's the formula for elastic potential energy. The halves cancel out, but I'll just leave them in case you guys aren't comfortable doing that. Mass of the block is 2.5 kilograms. It's 3.0 meters per second. Don't forget that that's squared. The stiffness was 360 newtons per meter, but I'm going to leave that out because I'm running out of space. And we want to find out by how much it compresses. Remember, the x is the spring compression. So that's what we're trying to solve for. So I'm going to type in all the left side on my calculator once. I go 0.5 times 2.5 times 3 squared, and that gives me 11.25. On the left, on the right, I got 1/2 of 360, which is 180. And then you got x squared. The rest is just math, guys. You go 11.25 divided by 180. It gives me some number on my calculator, and don't forget to square root it. And you'll find that x equals 0.25 meters or 25 centimeters. That's how you do number one. Number two says a 5-gram pellet is placed in the barrel of a toy gun, is propelled by a spring with, again, a force constant. That's the stiffness of 50 newtons per meter. That's been compressed 20 centimeters and released. Calculate the maximum velocity. So this is the velocity that the pellet leaves the gun. Again, I start by saying the total initial energy has to equal the total final energy. So this is the opposite of the first question. In this case, it starts on a compressed spring, and it ends up leaving that spring with some kinetic energy. 1/2 kx squared, 1/2 mv squared. The stiffness of this one is 50 newtons per meter. And it says it's compressed 20 centimeters. That's got to be in meters for this to work. Don't forget that that's squared. 1/2, it gives me the mass. The mass has to be in kilograms. That's 0.005 kilograms times v squared. And we're solving for v, the velocity that it leaves the gun with. So on the left, I go 0.5 times 50 times 0.2 squared. That equals 1. That's handy. Equals, over here, I got 0.5 times 0.005. And that's equal to 2.5 times 10 to the power negative 3, or 0.0025 if you prefer that, times v squared. So I got to go 1 divided by that. 2.5 exp negative 3 gives me 400. Then I'm going to square root that, and it should give me 20. Should get a speed of 20 meters per second. Pause this video at any time if you need to catch up and punch these numbers into your calculator yourself. We got a few more to go. Number three is tricky. And I don't know how detailed the solution is. Like I got these questions from some textbook resource years ago. So I know that there's answers and solutions there, but I didn't do those solutions or check out those answers. So I think that the answers are reliable, but the solutions, who knows? I used to use this question here as a test question, as an application question. So here it goes. A 30-kilogram girl goes down a slide at an amusement park, reaching the bottom with a velocity of 2.5 meters per second. The slide's 10 meters long, and the top end is 4 meters above the bottom end, measured vertically. So here's your situation. This is basically a triangle. Oh, I don't like how that did that automatically. How do I delete that? Anyway, I'll use that. I'll use that. There. No problem. So it's 10 meters long and 4 meters high. And it gives me some other information. So this takes you like step by step. So A says, what is the child's gravitational potential energy at the top of the slide? So it starts out really easy, but it's a tricky problem in the end. So you just go EG equals MGH, not a big deal. And you take her mass, 30 kilograms, 9.81 for G. And the height, make sure you don't use the 10, you're up a height of 4 meters. You punch that into your calculator and you're done part A. So I got 39.81 and 4. It gives me 1177.2 joules of energy. B says, what's her kinetic energy at the bottom? Now, normally when we're doing a conservation of energy problem, you would just say, well, it's got to be the same thing. But in real life, when you're sliding down a slide, there's friction. Some of that energy turns to heat, some of it turns to sound, so you don't get the same. We should get less kinetic energy at the bottom, and we can find it because it tells us her speed. It's 1/2, 30 kilograms, and it says she reaches the bottom at 2.5 meters per second. We don't forget to square that. So if we type that in, I should get a value less than that original gravitational energy. 0.5 times 30 times 2.5 squared. It's all the way down to 93.75 joules of energy. And that's how you do B. And you can see a lot of energy was lost. Most of the energy was lost due to friction. That's kind of the point of the slide. If you were going to conserve your energy, you wouldn't use the slide, you just jump off and let gravity just pull you down. The slide is there to use friction so that you don't come crashing down 4 meters to the ground or however high the slide is. C just says how much energy was lost. All right, so your energy loss is just going to be equal to what you had at the top, 1177.2 joules. Subtract what you had left at the bottom, 93.75 joules. That will tell you how much you lost. I'm typing that in right now, 1177.2 minus 93.75, and it gives me 1083.45 joules. I'm going to keep that number, but it's an answer, so I haven't been rounding these, so it's not going to match exactly what you've got if you scroll down to the answers, but it's going to be good enough, I hope, to show you how to do these problems. So that's C, done. Part D, calculate the frictional force. All right, so far it's actually not too bad. I think most of you probably could have thought your way to that and to that and figured out, all right, that's how much energy is lost. But now we have to calculate how much friction there is. Now, friction comes from work, right? Work equals force times distance. How much work did friction do? Well, friction took that energy out of there. 1177.2 minus 93.75. That's that 1083.45. 1083.45. So that is how much work friction did. That's how much energy was lost. And we're assuming that it went all to friction. I guess it's not that. Depending on the slide, I guess some of it could turn to sound. So here's the frictional force. How much distance was the frictional force present? Well, it's the whole length of the slide. So don't use the 4 meters. Use the length of the slide. Use the 10 meters. So I'm just taking that number and I'm dividing by 10 then, and I got 108. So the force of friction here is about 108 newtons of force. Anyway, that was, from the feedback I've gotten from students over the years, that was one of the tougher types of questions that I would have on the test. Now on yours, it'll be open book and you can look back to this. So just kind of bank this question in your head. This one that you can come back to and have a look at if you need to. Number 4. This one's real easy. It's just, I don't know why I even threw this one in here, but it gives you a mass. It's a 2,000 kilogram minivan. If you do that much work, how high is the minivan? So it's really just a throw in that will only confuse you if you're laser focused on doing a ET initial equals ET final problem. But really, you're just going 3.0 times 10 to the 4 joules equals the mass, which is 2,000 kilograms, times 9.81 times h, and you're just solving for h. I'll do that real quick just to say I did it. 3xp4 divided by 2,000 divided by 9.81, and it gives me that the height it's lifted is 1.5 meters. Unless I missed a decimal place in there somewhere, that should be the answer. The last one I'm going to do with you guys today is number 5. A 2 kilogram bag is held by a string and tied to the ceiling as shown in the diagram. 10-gram bullet traveling at 100 meters per second strikes the stationary bag. The speed of the bag after the collision is 0.8 meters per second. Assume there's no friction. Determine the maximum height in centimeters of the bag after the collision. It's actually a simple problem if you can get over one hurdle. Total energy initial equals total energy final. Which speed do you use? The speed of the bullet or the speed of the bag after the collision? And the answer is you use the speed of the bag after the collision. If you want to know how high up the bag goes, you got to start with the speed of the bag after the collision. So it is just starts with some kinetic energy, and it's going to swing up and then come to a stop and have some final gravitational energy. 1/2 mv squared equals mgh. That's the initial velocity, and that's the final height. You have to just ignore the whole, all that stuff. The mass of the bullet, the speed of the bullet has nothing to do with it. You need to know that it's a 2 kilogram bag, and after the bullet strikes it, it's going at 0.8 meters per second. Got my 2 kilograms here, I got my 9.81, and I'm solving for height. And that's it. That's going to get you this problem done. So you go 0.5 times 2 times 0.8 squared equals divided by 2 divided by 9.81, and it gives me a small value. I don't recognize the number I got, so I'm just going to punch it in one more time. 0.5 times 2 times 0.8 squared. I'm going to write out some more steps here. 0.64. 19.62 is 2 times 9.81 times h. 19.62. Now I got the same number again. It must be it. So I got my height of 0.033 meters, and that would be 3.3 centimeters, I guess. Anyway, you can scroll down. I don't think I made any errors there. I just don't recognize that 3.3 centimeters, which is what concerned me. So what I want you guys to do for today and Thursday and Friday is do the rest of them. Do the rest of them. So that's going to be 6 to 11. And as usual, feel free to email me if you get stuck at any point. 8, 9, 10, 11. Those are all good problems. And not all of your next tests, but a lot of it will be focused on this type of problem because really it incorporates everything, right? What did we use today? We used the work formula. We used the kinetic energy formula. We used the gravitational potential formula. We used the elastic potential formula. It's all in this one skill. So I really could have just a chapter assessment with just it. And I have done that before. I haven't decided what I'm going to do with you guys yet. It won't be till probably Wednesday of next week is when I'll post the chapter assessment for this. So just keep working away at this until then. Any of these questions you email me about, I'll get back to you as soon as I can, all right? That's all for now, guys. Get the rest of these done, and that's your work for the week. Once you're done the 11 questions on this, you are done physics for this week. Good luck.